apologize for the technicalities we had last time. Hopefully this time will go on smoothly. But you know, modern days technology. But then again, you know, we can all meet while everybody is sitting in your home and, you know, feel comfortable and relaxed. Apparently, we don't have that many more weeks to go, but I think we have only this week and the next week, and then that's it. But yeah, okay. So before we begin with the actual lecture, I went over your problem set, the last problem set, number 8, and I wanted to say a few things about that. So in question number 1, so let's call it a tutorial. Right? Can you see, what do you see? Can you see my screen now? I have, okay. So in problem set number 1, I ask you to prove the Gauss-Bonnet theorem. It's a fundamental theorem. And I really like it because I thought this is something which will make you think, and some of you did think, and some of you just told me that you were thinking, which makes it, I'm not fully entirely convinced about that. So the Gauss-Bonnet theorem, let's go over briefly, right? It's a powerful relation that holds for compact boundaryless two-dimensional spaces. So we talk about a two-dimensional space right now. We're not talking about n-dimensional space. And states that the integral of the Gaussian curvature over the space depends only on the Euler characteristic. So integral over space of K is 2 pi E. And I said that E is the number of vertices, minus the number of edges, plus the number of faces. Right, so if we have a triangle, right, then we have 3 vertices, edges is also 3, and faces is of course 1. Right, so the first thing is to realize that. And I actually told you that that K, the Gaussian curvature is related to the Ricci scalar by r/2. So that for a 2D sphere, then of radius r, then K is just 1 over r squared. So K is just the Ricci scalar over 2. So the first thing I ask you to do is to show that the contribution, so I gave you some steps on proving that. So the first thing I ask you is to show that the contribution to the integral from the apex of a circular cone is just the deficit angle of the cone, replaced by the singularity, by replacing the singularity of the apex by a spherical cap that joins smoothly at the cone. So it's really looking a little bit of an imagination, right? So we have a cone here. And the cone has some angle alpha, right? And then I told you, okay, now, of course, the cone, and we discussed that, is actually can be seen as a flat space, except from one point, which is the edge, right? So everything here is flat except for that point. And to get to that curvature of that point, right, we put a sphere, which we just stick inside the cone, right? And then, you know, from the center of the sphere, right, it would be here at 90 degrees. This is something which you surely know, right? And so the angle here would be pi over 2 minus alpha. Right, that's kind of obvious. So if we now look at the cone itself, so I'm going back to the cone, right? If I just put here the cone, right? This is alpha, right? This would be r, let's say. Then the radius of this circle here is just r sine alpha, right? So when I open up the cone, when I take this cone and I open it, right, then I'll have sort of a Pac-Man, shape, right? Because since I open it, this is R, so this is R, right? And the circumferences, right? The circumference. This is just 2 pi R sine alpha, right? And the deficit angle is this, right? This is the deficit angle. Okay. Right. So if I want to calculate this integral over the curvature, right? So the integral over the curvature, right? This is something which most of you did, is integral from cosine of pi over 2 minus alpha to 1 of r squared d cosine alpha times integral 0 to pi d phi times k, right? Which is just 2 pi minus sine alpha, which is of course exactly the deficit angle. I think this part most of you did properly, right? Now the second part, I asked, think of the fact that the same can be said of any vertex of a polyhedron. And some of you gave me some strange answers, such as, oh, I thought. I meant you to be a little bit more specific than that, right? So if I have a polyhedron, right, let's say a pyramid, right, then I have this, any vertex of the polyhedron. Now I can take it and simply open it up, right? So if I open it up, I'll have this 1, 2, and 3, right? If I change the color, right, this will be the purple, so this will be 1, 2, this is the purple, that's right. This will be the green one, and this is the green one. So basically, open it. So regardless of what I have otherwise, then I can look at this deficit angle that will give me the contribution from the vertex of the polyhedron. And then in part 3, I said, okay, after you realize that, and I don't think any of you are actually, but many of you didn't really go through it. And then I said, prove that the sum over all deficit angles of the vertices of a polyhedron equals 2 pi e. Now, some of you used some theorems, which I don't know where you took them for, but the whole idea was that you actually prove it yourself. And the proof is not that difficult, right? Because we're talking about any polyhedron, right? So this can be, this is also a polyhedron. So how can you prove it? So the easiest way to prove it, to my opinion at least, is to notice that any polyhedron, you can always divide into triangles, right? Because any face that you have that is not a triangular face, you can always divide it to triangles, right? So maybe I should do. So the number of vertices, what's the number of vertices here? Yeah.
4.
4 here as well. What's the number of edges?
4.
4, right? 1, 2, 3, 4. What's the number of edges here? What's the number of edges? Come on, guys. Number of edges.
6.
How many? 1, 2, 3, 4, 5. Those of you who thought of that enough, you should have no problem answering this, right? You thought of vertices and edges and everything. What's the number of faces?
1.
1, right? 1 face. What's the number of faces here in the right hand?
2.
2, right? 1 and 2. What's the Euler characteristic? What's the Euler characteristic? I don't know. You solve it yourself, guys. What's the Euler characteristic here? Yeah. What's the definition of the Euler characteristic?
E minus E plus F.
Yeah.
So it's 1.
And here?
1.
1 as well, right? So basically, when I take any face and I split it into triangles, right, I add up one edge. Every line I add up one edge and I add up one face. So I'm not changing the Euler characteristic. So any polyhedron I have, I can always think of it as a polyhedron that is made out of triangles. Right? Now, what's the advantage of doing that like that? Why would I be interested in doing it like that? Hey guys, I assume you took the time to solve this problem at home. What's the sum of angles in a triangle?
Pi.
Pi, right? So what's the sum of inner angles in a polyhedron? What's the sum of inner angles in a polyhedron, any polyhedron? Yeah. What's the sum of inner angles in this polyhedron here? I have to say I'm disappointed. I thought it's a beautiful problem. What's the sum of inner angle of a polyhedron?
4 pi.
How much?
4 pi.
Oh. After I divided the polyhedron into triangles, what will be the total sum of angles inside? For each triangle, it's a pi. How many triangles do I have? Guys, please, no cell phones now.
12.
How many?
12 triangles.
Well, that depends on the polyhedron, right? That depends on the number of faces, right? Just pi times f, the number of faces. And so what will be the sum of the deficit angles? What we had here? What will be the sum of the deficit angles?
Two pi minus pi f.
2 pi times what?
2 pi minus pi f minus the sum of the inner
Each vertex contribute 2 pi. They have v vertices. So it's going to be 2 pi times v minus pi f. Yeah? So for each of the vertices, right? Each of the vertices, right? You contribute 2 pi total angle when I open it, right? This is the sum, right? So 2 pi 1, 2 pi, 2 pi, 2 pi, 2 pi v minus, this will be the inner angle. The rest will be the deficit angle. Now, how is that related to the number of edges? How many edges do we have? How many edges does each triangle have?
3.
3. So how many total edges are we going to have? How many triangles do we have?
Maybe 3f.
Yeah, but is this the number of edges?
Minus e, the number of edges in the original.
Because each edge, right? And when we open it, I tell you, it's a lot about the thinking, right? Each edge is common to 2 triangles, right? Each edge is common to two triangles, right? So 3f is actually twice the number of edges that there is. So I can write it down as f is equal to edges minus 2f. And so the sum over deficit angles is 2 pi v minus pi f, which is 2 pi v minus edges plus f. Huh? Just 2 pi, the Euler characteristic. That's it. A little bit of imagination, not too much. Somehow, I don't know, some people try to make some shortcuts of various kinds, which is a pity, really. It's not a question of calculations that you need to solve, big integrals. But just seeing that, just having a little bit of imagination and seeing how you work out this a polyhedron. All right. More about this problem, right? In question number 2, you're asked to do to work out to calculate the proper time in an astronaut that orbits time t. that orbits in a Schwarzschild radius. All of you did it pretty much okay, only that some of you used the big shortcut by assuming it's a Keplerian orbit rather than just calculate the full, the Christoffel and the geodesic, which you could have done that. That was the point, that you actually do that. Of course, you end up with the same result, and that's fine, but I have a typo here somewhere in my answer, but it doesn't really mean anything. All right, that's what I had to say about this problem set number 8. Any questions about that? That was the end of the mini tutorial. Okay, now let's do a recap. So last time we started to do a recap, but then somehow my connection was gone. And then I told you that the solution I got from the computer guys was to turn things off and on again, which I did, and somehow miraculously worked out. It's really a black magic. So we're doing cosmology. So we said modern cosmology is based on the Copernican principle, which states that on very large scales, the universe is homogeneous and isotropic. Now remember, another thing that I know it was confusing me as a student, right? We're talking really about large scales, right? It's not the scale of the solar system. It's not the scale of the galaxy. It's not even a scale of clusters of galaxies, right? It's a very big scale, right? Which this is a valid approximation, right? So there is no real contradiction between the Schwarzschild solution, which is valid, let's say, in the vicinity of a very massive object, to this solution, to the Robertson-Walker solution, which is valid on a very, very, very large scale, when we cannot say that there is one massive object that controls everything, right? Now, I said that from a mathematical point of view, homogeneous and isotropic, meaning maximally symmetric space. So mathematically, this means a maximally symmetric space. Which implies a maximum number of Keeling vectors that are possible in that space. There's of course n for translations, plus n minus 1 over 2 for rotations, which is n times n plus 1 over 2. Right, and then we make some, okay, and then I said that I have to be a bit careful because, to be precise, Hubble showed us that the universe is not symmetric in time because it is expanding. So the future of the universe is not the same as the past of the universe, but we are only assuming it's symmetric in space. So the technical term is a space with a maximally symmetric subspace. Okay, so it's slightly more complicated, but not really. There's no point in getting into all these mathematical subtleties more than we actually need. And then we made some mathematical derivation. I don't know if there is a point of repeating them. And I argued first that for a maximally symmetric space, symmetric space, then we have that minus r lambda rho sigma nu delta kappa mu plus r lambda mu sigma nu delta kappa rho minus r lambda sigma mu rho mu delta kappa nu plus r lambda nu rho mu delta kappa sigma k lambda kappa is equal to r lambda sigma rho mu nu minus r lambda mu rho mu derivative with respect to sigma k lambda. This was a general property of the Killing vectors. And then I said that in a maximally symmetric space, general property of Killing vectors, but in a maximally symmetric space, we have k lambda is equal to 0 and k lambda nu is equal minus k nu lambda. I think the simplest way to look at it is to think of rotation in simple Euclidean space, right? If you think of a rotation around the x-axis, it will be a 0 minus zy, right? Which essentially saying k lambda, right, around the axis 0, but k lambda nu is minus k nu lambda, right? dk y over dz is equal minus dkz over dy. Right. So plugging this result in, we ended up, and a little bit of algebra, we ended up with a special, special structure of the Riemann tensor, and then that led us to writing down this Riemann tensor r lambda rho sigma nu as the Ricci scalar or alpha divided by n minus 1 times g nu rho g lambda sigma minus g sigma rho g lambda nu. And the Ricci tensor r sigma rho is 1 over n g sigma rho times r. So these are two results which hold only when we have a maximally symmetric space. So this is true in maximally symmetric space. And when we use the Bianchi identity, so plus the Bianchi identity, that led us to write down r lambda rho sigma nu as some constant. Sorry, I skipped that step. Using the Bianchi identity, we could write down 1 over n minus 1 over 2 r lambda sigma is equal to 0, which means that for n, the number of dimensions greater than 2, then the r, or r lambda lambda, is constant. So the constant curvature. And so we introduced a new curvature, which we call k, as n minus 1 times r. Oh, sorry, the opposite. R divided by n minus 1. And with that, we wrote down r lambda rho sigma nu as k times g nu rho g lambda sigma minus g sigma rho g lambda. So this is a general result that we obtain for a maximally symmetric space. Using that, we derive the Robertson-Walker metric. So we wrote down Robertson-Walker or W metric. Okay. Ps squared is minus pt squared plus some constant a squared t. So some constant that depends on the time. Gij psi pij. And what happened now? But again. Can you see my screen? Yes, okay, it returned. Hopefully this was just a small, and A of t has a name. It's called a scale factor. That's a factor that depends on the time that multiplies all the spatial part of the coordinates. Okay, so that means that, again, it kind of makes a lot of sense. We're saying that the spatial part of the coordinate are maximally symmetric, but they can evolve in time. So A of t tells us how much they evolve in time. Right? Note that this is the factor, exactly the factor that enables the universe to expand and shrink, right? Take all the coordinates and we can make them move in time, basically. We'll see what it means shortly, today or the next lecture. Right? And then, okay, we use the results that we derived here for the three-dimensional part, for the spatial part. So we call it R3. That's for the 3D part, spatial part. And we use the I and J to describe the spatial part. And then in order to proceed, we further basically repeated the results that we had in the derivative of the Schwarzschild metric by arguing that for a maximally symmetric space, it has to be, in particular, spherically symmetric. That implies spherically symmetric. And since we already derived the spherically symmetric solution, this is of course the Schwarzschild solution, then we made use of the result which we already derived to write down the Robertson-Walker metric. So use the derivation for the Schwarzschild metric to write down the Robertson-Walker metric as Ps squared is equal to minus Pt squared plus A squared of T multiplied by dr squared over 1 minus kr squared plus r squared d theta squared plus sin squared theta d phi squared. So this is the general solution that we have. So we have two unknowns here, or two three parameters at the moment. One is the scale factor, I of t, and the second one is its k. But then we noted that while k can take any value, in fact, it doesn't matter because we can always rescale the coordinates. So if we rescale the coordinates, such as k is rescaled to k over r over k, so normalize it. And then we can rescale r to square root of k, absolute value times r, and a to a divided by square root of the absolute value of k. Then the metric remains the same. It's unchanged. So in fact, although k can take any value in principle, we only care about three values, which are -1, 0, and 1. So k can be really -1, 0, and +1. -1 is called a negative curvature. Or open. 0, of course, no curvature, spatial curvature. Or flat. And +1 is called a positive curvature, or positive spatial curvature. Or closed. So these are the three options that we have for the spatial part of the universe. Now, and then I actually showed you that when you plug in k equal to 0, that's the easiest, right? If you put k equal to 0, then this is just the r squared plus r squared d omega squared. So this is just, Euclidean space. If I wrote this as the sigma squared, just to denote somehow the spatial part, then we end up that d sigma squared, so k equal to 0, that means that the sigma squared is just dx squared plus dy squared plus dz squared, and r squared plus r squared d omega squared. So this is just Euclidean space. So in that case, the universe is simply Euclidean. Now it may still change in time. It's kind of interesting, but it's still Euclidean. A way to think of how can it happen is an analogy that actually this is the one that I have invented myself, is that of a photocopying machine, right? You know, you can take if you want to photocopy a paper, I don't know if you do it anymore these days. But when I was a student, we were doing it all the time, right? And sometimes you want to shrink the information. So you take a page and you put like 50% or something, and you photocopy it, right? You're not losing any information, but everything becomes denser, right? Or you can make it larger, right? By putting the zoom option in the photocopy machine. You just need a bigger piece of paper. So essentially it's the same thing, right? It's flat and it will remain flat, just things can get in time smaller or bigger. That's for the k equal to 0. For the closed universe, k equal to 1, right? Then we can write down r equal to sine of chi, and then the spatial part of the Robertson-Walker metric, d sigma squared, can be written as d chi squared plus sine squared chi d omega squared. So this is really a three-dimensional sphere, something which is difficult to imagine, right? It's very easy to imagine a two-dimensional sphere like the Earth, right? But this is a three-dimensional sphere. Remember what we talked about in the one of the introduction lectures to this course, right? If this is the spatial part of the universe looks like a three-dimensional sphere, right? The meaning is that, like Magellan, right, many years ago, started to travel around the Earth. He went west and west and west and west and west, and eventually he ended up back to the place where he started from, which I think was Portugal or Spain, I'm not sure, right? So the same thing would happen in this universe, right? If we start traveling somewhere in some direction, or send a light ray. We travel and travel and travel and travel and travel and travel, and at the end, we will return back to where we are. It's a very interesting thought, I would say. At least to me. That's what it means if it's spatially, closed. It's a bit more complicated than that because the scale factor also changes during this travel. But conceptually, this is what's going to happen. And that also has a name. This is called the de Sitter space. Okay, so and the last option that we have is that k is equal to -1. So again, we can make a change of coordinates, write down r is equal to sine hyperbolicus of psi, and we ended up with this sigma squared is just the psi, I think. And the psi squared plus sine hyperbolicus squared of psi and the omega squared. And that, of course, corresponds to some three-dimensional saddle. The idea is that any two parallel lines will just diverge and get away from each other forever. And that's called the anti-de Sitter space, for obvious reasons. Okay, so these are the three options that we have for K, and I describe the three possible solutions for the Robertson-Walker metric. And then we said, okay, this is quite good, but this didn't tell us anything about the temporal evolution of the space, namely how the scale factor A of t evolves in time. And in order to get that, we actually had to plug it into Einstein's equation. So we went through the long way, which I shortened by writing it down for you in my lecture notes. And then after some algebra, so for the evolution of the scale factor, we had to plug this metric into Einstein's equation. Right? So we had to calculate gamma, mu sigma, and then the Riemann, and then the Ricci tensor, and ended up with RII, and the Ricci scalar, which ended up as equal to 6 over a squared, a dot dot plus a dot squared plus k, where a dot is just the a over the t, a dot dot is just the squared. And then on the right-hand side of Einstein's equation, now we could not assume it's a vacuum. So we actually had to write down the stress energy tensor for a perfect fluid, assuming that the universe is made of perfect fluids. Right? T mu is just P plus rho u mu plus P g mu. And because it's perfect, then there is no preferred direction. It's also isotropic, right? And then we ended up with T, just T mu is just minus rho plus 3P. And then we just plug it in after some algebra. And we ended up with A dot dot over A is equal to minus 4 pi G over 3 rho plus 3P, and A dot over A squared is equal to 8 pi G over 3 rho minus K over A squared. So these two equations are the two equations that we obtain after plugging the Robertson-Walker metric into Einstein's equation, and they determine how the scale factor evolves in time. They have a name. These are called Friedmann equations. Together with the Robertson-Walker metric, these are called the Friedmann-Robertson-Walker universe, or the FRW universe. So note that the evolution of the scale factor depends on three things, right? Apart from all the constants, it depends on the energy density, rho, on the pressure, and on the K, on the curvature of the universe. And this is pretty much as far as we did last time, although unfortunately I could not derive it directly. I just show you the derivation I did at home. And yeah. Any questions about that? Of course, I will give you access to my personal lecture notes after I fix some bugs that I found out in the derivation I made myself. Any questions? Okay, because now comes some really, really, really fun parts that we're going to discuss now. Let's look at what fun parts I'm talking about. Okay, so these equations tell us the global properties of the universe, essentially. So the first thing we do, right, you know, the scale factor is something which, some factor that multiplies all the coordinates. So we cannot really tell what its value is, but there is one thing which we can tell, and that is how much it changes, right? And the way it changes, actually we can tell what's the value, but we'll talk about it later. It has a name, so A dot over A. This is the rate of change of the scale factor. Does any of you have any clue of how we call this rate of change? Rate of expansion of the universe.
Hubble.
Very good. So this is after having Hubble. So this is called H. And that's called Hubble's parameter. Right. So again, you know, we can just take the ratio of A dot over A because we cannot really tell about A. Now note that the Hubble parameter can change in time. It's not something which is constant. It's something which, you know, since the scale factor is some function of time, then this is the Hubble parameter also changes with time. Now we are also defining what's called a deceleration parameter, call it Q, and is defined to be minus A dot dot over A dot squared. This is called the deceleration parameter. And that measures the rate of change of the rate of expansion, essentially. Now, how do we call the Hubble's parameter today, at present day? You've heard the name. Yeah. Are you talking? Is anybody saying anything? Because I don't hear you. Come on, guys. Turn on your mics if you want to say something. How do we call Hubble parameter today?
Hubble constant?
Yes, very good. And it's denoted with a small 0. H naught. That's called Hubble's constant. Hubble's parameter today. So everything which is today in cosmology is denoted with a small 0. Okay, so the reference time is today is 0. Today, this is called Hubble's constant. Which is great because there's nothing constant in it. Now, the measured value, so H0 is A dot over A. Today, T equal T0. Again, everything which is 0 in cosmology means today. So the measured value, I wrote down is 70 plus minus 3, but there is even a better measurement. It's called, the last one is 67.66 plus minus 0.42. And the units are kilometer per second per megaparsec. So it's a velocity divided by distance. Megaparsec, right? It's a unit of distance. Typical in cosmology. 1 megaparsec is 3 times 10 to the 24 centimeters, approximately. Okay, so, but it's enough to remember this is 70 plus minus 3, roughly. Now this is a measurement, this measure that I quote is a measure from the Planck data release. The last data released of the Planck satellite was back in 2018. I think that last week they released some update, but I haven't followed exactly if they made any change. I don't think they have. But that's roughly the value. Something like 70. Slightly less than 70. Why is that of interest? We'll get to in a few minutes. The 70 is another satellite dedicated mission, which is called the WMAP mission. We've studied the cosmic micro breakdown fluctuations. Don't know if we'll have time to discuss them this semester. Okay. So Hubble's constant is it's something which, of course, Hubble was the first one to measure. And since Hubble's time, which has been like nearly more than 90 years ago, then it's been extensively measured with all the best technologies that there are. And we'll see in a second why. Okay, so why are we interested in? So when we have Hubble's parameter, we can look back of the second of Friedmann's equations and write it as write as followed. So it's Hubble parameter. We write down this Friedmann equation, A dot over A squared. This is just H squared. So we can simply write it down as second Friedmann equation. Becomes 1 is equal 8 pi G over 3H squared rho minus K over A squared H squared. Okay, just rewriting the Friedmann's equation. And now we can define what's called the critical density. So it's really the critical energy density, right? So the critical Remember that rho is the density of energy. And conceptually, it's the same as the regular density, right? Rather than how many particles we have per centimeter cube or per meter cube, we're talking about how much energy there is stored in per centimeter cube or meter cube. So the critical density, rho C, rho critical, is 3h squared divided by 8 pi g. Right? So if we measure the Hubble's constant, today we can measure the critical density today. So today the critical density, and just write it the same color, right? So rho C, rho critical today, again, anything with a 0 means today, is just 3h0 squared divided by 8 pi g. So everything is a constant here, really, except from the Hubble, which we measure. That is 9.21 times 10 to the minus 30 gram per centimeter cube. Or, of course, there is a C here, right? So C squared. So you can write it down as 5.19 times 10 to the 3 electron volt per centimeter cube. Okay, so we basically measure the Hubble's constant, and then we change units and wrote it down in units of energy density. And the reason why we're interested in doing that is because this enables us to define what we call the density parameter. Right? It's called omega. And this is just the ratio of the density, the energy density, as we measure it to the critical density. So it's just 8 pi g over 3h squared rho, or just rho over rho critical. So we just normalize the energy density that we're measuring. Yeah. Guys, yeah. Yeah, question?
Stuff. So is the critical density the density where you say the universe will fall back in, like, or tear apart?
Wait, everything will be clear. We're doing things in an ordered way, right? Everything will be clear. So let's see. Remember, we have these Friedmann equations. This is the second Friedmann equation, which we wrote it down. We basically just renamed some of the parameters there. That's it. But now let's see. If rho is smaller than rho critical, what does it mean about omega? If rho is smaller than the critical density. By the way, I ask all of you to open up your cameras. I much more enjoy watching your faces than watching the black screen. What does it mean about omega if rho is smaller than rho critical? Huh? So maybe before that.
Omega is smaller than 1.
What? It's smaller than 1, right? Before I even write that, maybe I should skip the point. Right, so I'm looking at the second Friedmann equation. Now I can write it rho over rho critical. Right, this is what's written here. So this is just omega minus 1 is equal to k over a squared h squared. Right, same Friedmann equation. Right, I just wrote this as rho over rho critical. So that's omega. 1 goes to this side, and k over h squared will go to that side. Fine, right? Not particularly problematic. Then we have the following, right? So if rho is smaller than rho critical, that means that omega is smaller than 1. So if omega is smaller than 1, what does it mean about k? What does it mean about K?
It's negative.
It has to be negative, right? Because A square and H square are necessarily positive. So if it's negative, then what value does it take?
-1.
-1. So what does it mean about the universe that we live in?
It's open.
Open. If rho is exactly equal to the critical density, what does it mean about omega?
1.
1. What does it mean about K?
Close.
No. What does it mean about K?
Equals A squared H squared.
What does it mean about K if omega is equal to 1?
It equals A squared H squared.
No, it's not. What does it equal to?
0.
How much?
0.
0. Right? If omega is 1 and omega minus 1 is 0, then K has to be equal to 0. So what does it mean about the universe?
Flat.
Flat. And if the density, the energy density is greater than the critical density, what does it mean about omega? Yeah?
It's greater than 1.
Greater than 1. What does it mean about K? What does it mean about K? If omega is greater than 1, I don't care by how much it's greater than 1, right?
Positive.
What? Positive, right. So K, but if it's positive, then what value does it have?
1.
1, right? You have only 1. Because I don't care if K is 27, then I can always normalize the coordinates. What does it mean about the universe?
Close.
It's a closed universe. Right? So the value of omega, right, the density parameter, is something which we can measure in principle, right? If we know what happens in the universe, if we know the expansion rate and we know what is the energy content of the universe, right? And that actually tells us which of the 3 possible solutions of the Robertson-Walker metric, so geometry, sorry, which of the 3 possible geometries described by the Robertson-Walker metric we actually live in, right? So now you can understand why people are making great efforts and spending a huge amount of money in trying to measure these density parameter, right? The density and the critical density. Now, does any of you have any clue what is the best known value of omega today? Does any of you have any idea? People are using a lot, spending huge amount of money on that, huge. I see that you're saying something, but I don't hear, so maybe your microphone is closed. Check out your mics. Does any of you know what is the measured value of omega? Does any of you want to guess?
1.
Remember, 1, yeah? A priori, there is nothing in the theory that tells us what should be the value. Right? A priori, there is nothing in the theory that tells us what the value should be. It can be anything. So here is the measured value. 1.0023 plus minus 0.0055. Pretty cool, isn't it? So the true answer is we don't know. the universe we live in is consistent with being flat, but is also consistent with being open or closed. It is a very big question, very big open question of why the value of omega is so close to 1 and not 0.15 or 239. Now, if you've heard about the idea of inflation, this is one of the motivations. This is one of the strong motivations of why people came up with this idea. In order to explain how can it be that the universe today is so close to being flat. These are all the measures that we have. In fact, it is consistent with being flat. Cool? Very cool, huh? Okay. That's what we know, and people are spending a lot of money on that, and they will continue to spend a lot of money on that. But that's not resolved, and we don't really understand it. Okay. And when I say we, I don't just mean myself. I mean, there is nobody who understands it. There's a Nobel Prize waiting for the one who managed to prove what's going on here. Okay. In order to further proceed and see how the universe evolves, we need to look at the context of the universe. Okay, so the context of the universe, right? We have to start with the stress energy tensor, which we wrote down previously. Now, what did I do? Okay, I can write down T mu, right? That's a diagonal of minus P, minus rho, P mu is just P plus rho, mu plus P. This is the diagonal part. So now we can look at the conservation of energy. Now, conservation of energy, I want to remind you, is just 0 is equal to mu 0. Yeah? That's how we write conservation of energy in a covariant form. If you don't feel comfortable, then play with that a little bit at home until you feel comfortable with that. Right? I think we derived that, right? When we spoke about stress energy tensor. Did I derive it for you? Euler equation, conservation of energy, that's what it is. That's, I did not do that. I cannot, I don't know who you are, but please turn on your mic. I think there was one of you that tries to say something, but I don't hear you. I don't hear you. Can you hear me, by the way?
Yes, we can hear you.
Okay, good. So, okay, so this is the conservation of energy. This is how the conservation of energy equation looks like in the covariant form. So this is just d mu 0 plus gamma mu 0 t 0 minus gamma lambda mu 0 t mu lambda. That you know, that should be familiar with to you, right? We did covariant derivative here. So just plug it in. This is just t mu 0. We're just going to get that is a minus t 0 rho. And then for the gamma mu 0, which we want to remind you that we did this derivation last time as part of deriving Friedman's equations. I wrote it down for you. Gamma 1 1 0 is equal to gamma 1 0 1 is equal to gamma I 0 I gamma I 0 I 1 2 3 is just A dot over A. Right. So So we end up with the minus 3a dot over a e plus 4. Since we only have diagonal terms, and we have 3, so we go over 1, 2, 3. And there's a minus sign here with the p. Oh, sorry, no, the p, we have a minus because of the minus here. Because of the minus here, and for the rho term, we have a minus rho. That's why we have this minus. Okay, so we have an equation which relates the scaling factor change A with P and rho, the pressure and energy density in the universe. So in order to make a progress, we need somehow to connect the pressure and the energy density. Now, what equation connects the pressure and energy density? What do we call such an equation?
Can you repeat the question?
Sorry, which one?
Can you repeat the question, the last question?
What equation? We have an equation. In order to make a progress, we need to somehow connect the pressure and the density, P and rho, right? How? What equation that we know in physics is an equation that connects the pressure and the energy density? You've seen that. You use that, not in this course maybe, but in other courses of physics.
Continuous equation?
No, no continuity. We're talking about pressure and energy density. Yeah. It's called equation of state, right? Equation of state connects pressure, density, and temperature, right? So density and temperature is really energy density when you think of it for a second. It's physics, right? Behind all this mass, now is the time that we actually do physics. So it's the same physics that you know of, right? So P and rho are connected via the equation of state. Okay. Again, if you don't feel comfortable with your thermodynamic things, right? Again, you just remember, right? It's a P is a pressure, rho is energy density. So just the density times the energy per particle, right? The energy per particle is really an association of the temperature. The temperature is a measure of the energy per particle. Right. Now we use again the fact that in cosmology, we can treat the matter or gas as a perfect fluid. So we have a perfect fluid equation of state. Right? So we have a perfect fluid. And the perfect fluid equation of state will read something like P is linearly proportional to rho. So the pressure, it depends on the energy density times some omega, some constant, which is independent on time. Yeah? Okay, think of that for a moment and make sure that you fully understand what I'm saying here. Somehow I feel that a lot of you are not fully following, which is a pity. A lot of you are not with open cameras. And I don't know, it's a pity because I think this is kind of a really fun part. So if we have that, I can use this equation here, right? This is equal to 0, of course, right? I can simply write it as the rho dot, right? This rho is just rho dot. So I have a rho dot over rho is just minus 3, 1 plus omega, a dot over a. Right? If I just write down P is equal to omega rho, let's plug it in here. So I have 1 plus omega rho, and then I can simply write it down the way I wrote. Right? Rho dot over rho is just minus 3, 1 plus omega a dot over a, which is something which we can integrate immediately and get down that the rho is just proportional with some proportionality constant to a, the scale factor, times minus 3, 1 plus omega. Okay, this is pretty straightforward. Okay, so this is what I wrote here, the conservation of energy, and using the equation of state, which for perfect fluid, I just said, okay, the pressure is just depending linearly on the energy density. Okay, now I can ask myself, okay, what do we have in the universe? Right, we said the universe is a perfect fluid, right? But this is kind of a general statement, perfect fluid, right? So what do we have in the universe? So what is there in the universe?
Matter.
Matter, right? What do I mean by matter? What kind of matter? What do you mean by, when you say matter, what do you mean?
Atoms.
Dust, right? What about dust? Now we talked about dust. What is the pressure of a dust? Guys, what is the concept of a pressure? When we say that there is a pressure, what causes the pressure? If I put some gas in the volume, right, what will be the pressure inside the volume? What physically causes the pressure? Not what will be the pressure, that we have to calculate. What causes the pressure?
Force.
Yeah, and what gets this force?
Momentum.
Interaction
Interaction, right? Interaction of what?
between the particles.
Between the particles and the walls, right? The particles hit the wall, they exchange momentum, right? And that basically puts a force on the wall, which we call pressure. Right? Pressure is essentially a force per unit area. Right? Remind you from your first year, you know, when you thought of these concepts, right? Pressure, right? You have some molecules. Right? They move randomly. Sometimes they hit the walls. When they hit the walls, they can extract, and you know, if I put a valve here, right? Some particle hit the valve, exchange momentum. That puts some force, and we call this pressure. Right? Now, what about dust? What can we say about dust?
Zero.
Zero pressure, right? P is equal to 0. Just resting there. There are no interactions, right? Or you can think of matter that is, you know, in the context of cosmology, we can think of matters in stars. It's not interacting with matters in other stars. They don't exchange momentum or anything like that, right? So again, so this is a dust. Pressure is equal to 0. So what is omega?
Zero.
Zero, right? So again, the examples will be anything that is ordinary matter, anything that is not moving relativistically. Right? Matter in stars, matter in galaxies, just some interstellar dust. This is just dust for me, right? And it doesn't cost any. Right? It doesn't have any pressure, so we call it matter. Now, if the energy density in the universe as a whole is mainly held by this matter, then how do we call it? Not a very difficult word. That would be called a any suggestion? So if the energy density in the universe is dominated by dust, we call it very simple, matter-dominated universe. Right? Simply because there's always radiation, right? But the radiation could be negligible in terms of. Now, how would the energy density of the in a matter-dominated universe change in time, or change with the scale factor from here? How would it change with the scale factor? I'm really worried, guys. I'm just showing you the equation. It says omega equal to 0. It says this is the equation. So you just have to plug it in your head. But nobody's answering. How is there's no hidden things here in this. How is this energy density changes with the scale factor? Okay, what's the problem? Why are you not answering?
To the
A
power
בחזקת
minus
מינוס 3. A בחזקת מינוס 3.
-3, thank you. Right, it goes a to the power -3. Right, omega is equal to 0. Plug it in here or in here. When you get that rho, matter-dominated universe goes with the scale factors 8 to -3. So what would be the physical interpretation of that? Yeah. Quite close. What's the physical interpretation?
הנפח גדל, הצפיפות יורדת.
Thank you. Let's say it in English, right? So you have a volume element, right? There are some dust inside. Now the volume element increases with the scale factor because the scale factor multiplies that. The number of particles have not changed. Right? So obviously the density of the particles has gone down. Right? That's it. It's a pretty straightforward conclusion, right? If the universe expands, then the density goes down. That's all. Right? The scale factor A multiplies each of the dimensions here. Right? This is x, then x prime is just ax. Right? This is y prime is just a y. And the same for z, of course. Right? Okay, Is this the only thing we can have in the universe? What else can we have in the universe?
Radiation.
Radiation, right? What do we mean by radiation? What's the difference between radiation and matter? So when we speak of radiation, what do we mean?
Energy.
No, we actually speak of two things. Energy, matter also have energy. What is equal to mc squared? What's the difference then? What do we mean by radiation?
Laptop.
What?
Laptop.
I could not hear you.
Laptop include photon and neutrinos.
Photon and neutrinos, right? So one is electromagnetic radiation, right? Photons. The second is actually everything that moves relativistically. So it could be neutrinos, could be massive particles, but they're light and they move in relativistic speeds. So also relativistic particles, such as neutrinos, they also consider to be radiation, right? For our purpose. And okay, now we need to derive the equation of state. So there's various ways of deriving the equation of state. I would say the correct way, there's more than one correct way, right? So the way that you should do it is write down the stress energy tensor for radiation, which I think I have written it for you. I hope I have, right? 1 over 4 pi f mu lambda minus 1/4 g mu f lambda sigma f lambda sigma. I think we derived that when we spoke about the stress energy tensor in special relativity. Did I derive it for you? You're not willing to admit it? It's very easy. I'm going to check out my lecture notes to see if we covered it. I think I have. I'm not 100% sure at time to go through it. And then when we take the trace, T mu, right, is just 1 over 4 pi. F mu lambda minus 1/4 times we have 4 because of the trace of the G, F lambda sigma, F lambda sigma. So this is simply 0. Now the trace, you remember, is just minus rho plus 3p of the stress energy tensor. So we ended up, this is equal to 0. That p is equal rho over 3. That's the equation of state for radiation. So this is the way you should derive it now, but there is also the first way students should derive it. So the first way students, we can say, going back to this example that I gave you of a box, right? Alternative derivation, right? You know, the energy is related to the momentum P via the energy is just P times C, right? That's momentum. Now the pressure extracted by n molecules hitting the boundary of a box, right? There are many more molecules going in various directions, right? Is 1/3 times the total number divided by the volume times the average of the momentum exchange times the velocity. But the velocity is just c, so it's just 1/3 m over v, the energy. This is just the energy density. In any case, okay, think of that. That is something we should be able to do after you finish the first year. So a universe in which the energy density inside radiation dominates is called a what? Very difficult term. It's actually not very difficult. How do we call it? I'm quite worried that you're not participating. If the radiation, the energy density in the radiation dominates over radiation energy density in the matter, how do we call such universe?
Radiation dominated.
Yeah, thank you. That's called the radiation dominated universe. What is W? What is W here?
Third.
1/3, right? So what is the change of the energy density with a scale factor A? If W is 1/3.
-4.
-4, very good. Rho R goes to A to -4.
Asaf, can I ask something?
Yeah, you can.
You keep talking about walls, but the universe doesn't have walls, right?
Yeah, that's true. But when you talk about energy density, you can take, you can define a wall and see what happens, a volume element and see what happens inside this volume element. But that's why the correct way of deriving it is using the stress energy tensor, which I just did derivation here. I just told you that you'll get the same result if you do it. You think of it in terms of molecules hitting the wall. Okay. I thought it could be that's confusing. If you find it more confusing, then forget it and just do the correct thing. Stress energy tensor. If you get confused with all these tensors, at the end of the day, they will give you up the same equations that you're used to without them. They will just do it quicker and with much less chances of being wrong and much easier to generalize to relativistic cases and things like that. Okay, now where we are. So the energy density of the radiation, when A is increasing, right? The energy density of the radiation falls off faster than the energy density of matter. Mm-hmm. Then the energy density of matter as A increases. So physically, why this happens? Why this happens? Why is it going on faster?
Because of the power.
Because of the what?
The power, -3 to -4.
Yeah, the -3 to -4 tells us to go faster, but physically, it's a question of physics, not in looking at the numbers. Why physically do they lose energy faster?
The wavelengths of the photon become grower.
Very good. So you have this loss of the density as the universe expands. The density decreases, but there is also a redshift. Since the universe expands, they're going slower and slower in this expanding universe, which is another source of energy loss. So they're getting slower, right? That also have a very interesting implication, right? We know today, for example, if we look at the universe, where is most of the energy, in matter or in radiation? Where is more energy, in the matter or in the radiation? When you look at the universe around you?
I think matter.
Matter, right? By far. Where is most of the energy of the radiation?
In space.
No, in space, in the cosmic microwave background. But you have radiation from the sun, you see radiation from the stars, right? But as far as energy density in the universe as a whole, most of the radiation that is in the universe comes from the cosmic microwave background, right? But today we know that raw matter, raw matter over raw radiation is about 10 to the 3 or so. 10 to the 3, depends how you count. 10 to 3 to 10, yeah, I think it's some few times 10 to the 3. But this is today. What we just show is that as the universe expands, right, the radiation loses its energy density faster than the matter. So if we go back to the past, it was not always like that. There was a time in the past, in the history of the universe, in which the energy density in the radiation was in fact greater than the energy density of matter. Right? In fact, in the past, energy density of the radiation was dominant over the energy density of matter. Then it switched. So the universe was once radiation dominated, and then it became matter dominated. Right? Now, is that all? Or is there something else? Is there anything else in the universe that might have an energy except from dust, matter, and radiation?
Dark energy and dark matter.
Dark matter is part of matter. We call it part of matter.
Energy.
So dark energy, right? Now we didn't speak about dark energy. Well, I did actually, I mentioned it. Right? I say this is a vacuum energy. This is energy that is stored in the vacuum. Right? So it's called the vacuum energy. Okay, now I'll just say it because we ran out of time really. And I want to spend more time on that than we do now. I'll just say it, right? That's the addition of the cosmological constant, right? Right, so we wrote down Einstein's equation, G mu nu as 8 pi G T mu nu minus lambda G mu nu, right? So we can think of it as a universe without any cosmological constant, but energy momentum tensor of the vacuum, right? So we have a T mu nu of the vacuum is equivalent to writing T mu nu of the vacuum as minus lambda over 8 pi G G mu nu. And then we can write down G mu nu as 8 pi G T mu nu plus T mu nu of the vacuum. So this looks exactly like a perfect fluid. This is a perfect fluid. But with rho, which is equal to minus P, is 8 lambda over 8 pi G. So what is omega in this case? What is omega? Huh? What is omega here? P is equal to omega rho. What is omega?
-1.
Yeah, -1. This is nothing to do. There is no gas or anything that you've ever seen that has this negative equation of state coefficient. And what does it mean about the evolution of the energy density of the vacuum? Rho lambda proportional to what? A to the what power? To the what power? Huh?
0.
0. Independent on the scale factor. Right? Now, here is something really interesting, right? The energy density of the matter, as the universe expands, right? They expand, right? The energy density of the matter goes down. The energy density of the radiation goes down. What happens to the energy density of the vacuum itself? Not going anywhere. Right? Such a universe is called vacuum-dominated universe. Now, do yourself a favor. Think of that. You haven't encountered, if you haven't seen that before, right? In everyday life, you never encounter anything which is even closely resembles this. Right? In fact, the more vacuum you have, the more energy is in this vacuum. So it's very counterintuitive. You never see anything that looks like omega negative in everyday life. All right, I took already 15 minutes away from your time, but partly because I wanted to do a lengthier than average recap because of the technical problems we had last time. So hopefully this compensated for that. Any questions? I got a bit concerned that many of you have not really participated. I was expecting much more because this is not a particularly difficult material. Certainly not technical and mathematical as we had previously. There's a lot of fun. There's a lot of physics. So review this material, make sure everything is clear in your head. And I'll see you all on Thursday. Any questions? No? Then thank you very much. Have a great rest of the week.